Now, I have been recording the previous lessons, a couple of them, but today it's very important that we did the recording because how many? 6, 9, it's only 4 of you missing. So 4 of you missing, so hopefully we won't need to repeat that session. Yeah, because that's a waste of time. So I sometimes do that when half of the class is absent. The next period I repeat it again, and it's a massive undertaking today anyway. Hopefully we'll go through it. We'll talk about satellites today. So can you try to look a little bit more enthusiastic about it, Kevser? Yeah.
Let's do this.
Yeah, let's do satellites. Yeah. You're making fun of satellites, but I mean the class, but your life relies on satellites. All right? Oh, it's a deer time. That's right. But we already started. That's all right. Anyway, it's only 6 minutes left anyway. You want to read stuff? 1 minute? We start as 1 minute. All right. Look. So, yeah, the satellites are extremely important. All right. They're mainly for communication purposes. But can one of you find a photo of all of the satellites in space? Do you remember such a photo? I have seen a photo of all the satellites around the Earth with their paths, drawn. That's quite a what should I say, pollution, satellite pollution. Anyway, but the good thing about satellites is once you put them there, you don't need to do much about them for a long time, let's say 20, 30 years, depending on the altitude. If it is a low Earth satellite, you have to. But it is a higher orbit satellites, they can pretty much stay there forever. Yes?
So you know how, speaking of satellites, you know how one of the satellites detected like 7 new planets and 3 of them?
Yes.
Do you think they actually will?
The 7 planets?
Like for us to get there, it's really hard to start coming like.
Yeah, the 7 planets. Yeah, there might be life-like or conditions available for life in other planets. It's possible. I mean, technically it is possible that there is an Earth-like planet. But whether there is life in that Earth-like planet or not is a completely different story. I believe life is special and started by someone outside what we touch and what we feel. So yes, you may have Earth-like planets out there, but to have life in those planets like we do life in here, it's a completely different story. Not because there's an Earth-like planet means that life is going to emerge by itself, because I don't believe the idea that life simply initiated itself from nothing or from just from some chemical substances. Anyway, so yeah, but that's obviously the hot topic these days, that whether there's an Earth-like planet, and they can look at the Earth-like planet and see some forms of life, that emerge there. But this is the hot. Well, it's obvious that we need a breakthrough. So with the current technology, it doesn't look possible. It doesn't look possible to go there with the current technology. But who knows? Who knows? Maybe some of you might find something different, that a breakthrough in science. And then that might be possible. But with the current technology, it doesn't look very, very, doable to go there and to actually check whether there is life or not. Anyway, so I think we have finished the read time, right? Reading time, deer time. already. All right, good. Now, remember we talked about Newton's thought experiment yesterday, all right? It has a lot of issues, but technically, after some ifs, you know, then such a path is possible, provided that you give that particle a great velocity, then the particle can actually start orbiting around the Earth. And if the velocity is greater than that, then it becomes an elliptical orbit, and so on. All right, so we talked about that yesterday. Now, when we look at what actually is happening, is no different than that. So this is the Earth, and this is an astronaut orbiting. So it's no different than simple circular motion. So the astronaut is doing nothing but traveling at an orbital velocity around the Earth. So it is falling on Earth. It's not traveling. The astronaut is not traveling in that direction. Right? So that is the intended path. Right? That's the direction of your velocity, right? So he actually tends to travel that way, but do you think he managed to travel in that way? No. Because of Earth's attraction, he ends up changing its path. So say he comes here, he comes to that point, all right? He then wants, in this point, this is his velocity, same in magnitude, different in direction. Then he intends to travel that direction. Right? But it's not going to happen. So instead, because of the pull of the Earth, because of the gravitational pull on him, which is what we call weight, he ends up kind of trapped in this circular path, and we call it an orbit. Right? But you need to remember that the astronaut's velocity is always tangent to the path, which it happens in circle. We studied circular motion last year, right? No?
So does that happen?
Whoa, what do you mean? We didn't do circular motion before? Wow.
So does the same thing happen with like the planets when they're orbiting the sun?
Yes. Pretty much the same. Planets orbiting the sun, satellites orbiting the planets, or stars orbiting the center of the galaxy, or the galaxies orbiting the center of the universe. It's pretty much the same thing. Oh, we didn't do circular motion. It's a shame. I thought we did circular motion. Anyway, all right. So let's have a look at circular motion then. Now, circular motion is quite an interesting one, because in circular motion, the direction between force and velocity is at right angle. Let's remember a regular case of, let's say, an object on a frictionless surface. You apply a force, all right, to this object, and then it will gain some acceleration, which will be directly related with the force and inversely related with its mass, right? So after a while, all right, if you look at the same object after a while, you will see it will acquire some velocity. But the thing is, it might be the other way around. If you push an object opposite to its direction of motion, all right, let's look at this scenario. Let's say you have an object traveling at a velocity, and then you apply a force, and you cause this object to stop. then the object will have an acceleration in the direction of the force, which means velocity, acceleration, opposite means slowing down. Remember that? Velocity and acceleration opposite to one another, you have slowing down and possibly stopping. All right? Here you have speeding up, here you have slowing down. But the thing is, the force and velocity and acceleration are pretty much on the same line. All right? On the same axis. Either in the same direction or in the opposite direction. All right? But they're in the same line. So that is what makes us quite simple to visualize it. But when it comes to circular motion, it's quite complicated because an object doing circular motion with a velocity, all right? Now, because of this centripetal force, whatever the cause of that force might be, it might be you are rotating a rock around your head, or it might be a satellite orbiting around the sun, or it might be a car taking a turn. Regardless, the force, the centripetal force, is towards the center. So you see there's a 90-degree angle between them. So this is the condition for circular motion. So when you have this, you have circular motion. When you have this, you don't have circular motion. You have linear motion. When you have this, you have linear motion. But when you have this, with the force and the velocity making right angles to one another, all right, then you have circular motion. All right, what happens to this object? Let's say it makes a quarter of a turn and comes here. That will be the velocity, girls, and that will be the force. You see? All right. What about somewhere here? That will be the velocity, and the force is still towards the center. So what we say is the force and velocity constantly changing direction, but not magnitude. You see that? The force and velocity are constantly changing direction, but not the magnitude. So let's write that down. The condition, let me write this is an important sentence. When the velocity and the net force are perpendicular to one another, sorry? All right. If they are perpendicular, there's no circular motion. The condition for circular motion is they must be perpendicular. All right. If they're not perpendicular, it's not circular motion, it's something else. But for circular motion, that is the condition. So let me say when. So the condition for circular motion is the velocity and the net force are perpendicular to one another. Yep. And we can also say that their direction constantly changes. It's not constant, constantly changes, but their magnitude stays the same. So that is the condition. Let's do a different color for that one. All right. Now we'll come back to this page later. But why don't you look at these examples? All right? There are 4 examples of different objects doing circular motion. Next page. There are 4 examples of objects doing circular motion. The first one is a hammer. All right? Now, just a second. Yes? No. This is called a hammer. It's not a hammer, or it's just a spherical metal ball, right? But it's for some traditional reason, it's called a hammer. Maybe we call it hammer because of some other reasons. Anyway, so that's a hammer, all right? So you hold it. So there is a rod attached to the hammer and your hand, and then you turn around it. You turn around it, and then the hammer, you rotate the hammer on your waist level or a stone above your head. So it does circular motion, right? So it's circular motion. But where do you think the force is coming from? Centripetal force. The force is coming from, in this case, what do you think that provides the force? Instead of the hammer going straight, instead of the hammer going in that direction, it stays in the circle, right? Why? What is holding it in line, in the circle? Nijat? What is holding the hammer in the circle instead of going like flying off? Why the hammer, stays in the circle instead of flying off? Sorry? There is a force, yes, but what is the source of that? Where is this force coming from? No, look, centripetal force, yes, centripetal force. Centripetal force. I don't know if it is force is, girls, all right, girls, is the net force. So centripetal force is equal to F net, which equals ma. All right? But it's something like that. The car is moving, there is a net force, but where is the force coming from? From the driving, from the engine, from the friction. Where is the force coming from now as I walk? From the friction, because if there's no friction, I can't walk. All right? So the net force, or the centripetal force, is the vector sum of the forces. But where is this force coming from in this example? What's the force? What's the actual force? You know the force is a push or a pull, remember? So what is the source of the force? Yes? The arm, yes, the arm certainly. The arm and the rope, tensions. In this case, it's the tension force. So in this case, it's the tension force, tension. So it is the tension force in your arm, and in the rope that provides the centripetal force required to stay in the circle. Now careful, the centripetal force, so when you are asked what is the force, when you say centripetal, it doesn't make sense. Because it's like net force, it's the net force, but what produces the net force? Why do we have this net force? Is the answer, all right? So it's very important in circular motion questions that you know the source of the centripetal force. It's always, most of the time, it's that makes it a bit tricky. The rest is maths. All right? Looking at this example, Anika, a satellite orbiting around the Earth. What is the source? What is the source of that circular motion? Because I know that is the orbital velocity of the satellite. But instead of going in that direction, instead of going that, it keeps being pulled back to the circle. So there must be a force. Keeping the satellite in that circle instead of, flying off. What is that? It's the gravitational force. It's the gravitational force exerted on the satellite by the Earth. On the satellite. So in this case, it's the gravitational pull. Girls, can you visualize that? Any moment, any location, the satellite is saying that please leave me alone. I want to just go in the direction of my velocity, right? This is what you want to do. You want to just fly off. You are adults anymore and you just want to fly off the house and want to leave your own house. But your parents are saying, no, you can't go anywhere, right? You're stuck to us and you just circle around the house. Not a good analogy, but kind of like that, you know? You just want to, look, the satellite wants to break off the connection and wants to go into space and explore other planets. But you can't do that. Always pushed back, you know, to stay in this circle. So that force, can you see this force is centripetal? Centripetal means center seeking. Center seeking. So that force is actually pushing the satellite instead of going to stay in that circle. So that's why we call this force centripetal. So this force is always towards the center. Making sense? Good. Yes, Kesar? Now, looking at the car. Again, it's the same thing. With the car, wants to go in a straight path, all right? But it's not. It's taking a turn, all right? It's taking a turn because the car wants to take a turn, but its velocity is straight, not circular. You can't have like circular velocity. There's no such thing. There is angular velocity, but there is no circular velocity. It has to be straight, right? As we know it. But it's taking a turn. Where do you think the force is coming from? From the friction. Think about it. Do you think the car can make a turn if you don't turn the wheels? Or you turn the wheels, all right, but there's no friction, like ice. Or the tires are flat, or you're traveling too fast, or you're making a very sharp turn. So there are a lot of things to go wrong for the car to go in a straight line rather than taking a turn. All right? But we rely on friction. But the friction has a limit. If you want to take the turn too fast, you fly off. Because the tires say, look, I can't produce that much friction. There is a limit, you know, the car can produce a friction. Between the tire and the road, there is friction. But there is a limit to that. It's not infinite, like infinite. So when you pass that limit, let's say you are too fast, and the tire cannot produce the friction anymore, and instead of staying in the circle, you go in the direction of your velocity. If you are going too fast, or your tires are flat, or the road is wet or oily, or you want to take a very sharp turn, that might be the case, yes.
So does the car still like turn a little bit before going off?
Yes, certainly. Yeah. It certainly will turn a little bit. No. Well, it depends on your speed. If you are like taking a turn with 200 kilometers an hour, right, you might not feel any turning at all. It just goes straight. Because that's what you expect from the car. The car is traveling in that direction at 200 kilometers an hour, and you turn the wheel. Just because you turn the wheel doesn't mean that the car is going to obey. Because it needs friction, and at that velocity you require a lot of force to stay in the circle. Or what about this thing? What is that thing called? The rotor? Gravitron. Is it gravitron? Gravitron. All right. So this thing. So do you have this in Luna Park? You can tell. Not this one? Yeah, the festivals. Yeah, that thing. Royal Melbourne Show or something, was that?
Yeah, they have that Melbourne show.
Yeah, so anyone tried that before?
Yeah. It's so fun. So you just
Yeah.
lift up the wall, you can turn around, you can do anything, but you're on the wall.
Yeah, on the wall.
You lift up your arm and it goes like that.
Yeah, exactly. So, now in here, what do you think produces the centripetal force? It's the normal force from the wall. Normally, there's no such force. There's no such force. But the thing is, because this thing, whatever we call it, this platform is rotating, and you are rotating together with it, you just want to go in the direction of your velocity, but you don't, because you can't, right? You can't. I mean, if you climb off, you can. If you climb here, you know, you will fly off, right? But now you can't. You can't just go in the direction of your velocity because the normal force, or The wall is pushing you to stay in the circle. Now, the circular motion, there are other examples of circular motion, but the key point is there must be, there is, if there is circular motion, there is velocity, and there is the center-seeking force, centripetal force. But the centripetal force is not a good answer. You need to say the source of that force. In this case, it's the normal force. In this case, it's friction. In an earth example, it's the gravitational force, or in this example, it's the tension.
So
Yes.
the centripetal force, the source is the normal force. For normal, that
Or
makes sense.
for this example, centripetal is the normal force. Or if we're going to say this is going to be called the Fn. For this one. For this one, but for that one, it's friction.
So, okay.
All right? Look, the question might be like that. All right, the car is taking a turn, and that's the acceleration. What is the centripetal force? Then you do m times a. And the next question might be, all right, what is the, not the centripetal force, but the question might be, what's the friction force? Then you know the friction is the centripetal, so you know the formula for centripetal. You find the centripetal, and you say, all right, centripetal is the friction. We will do examples in a moment, but before we do that, why don't you have a look at this one? There is some comparison of common circular motions, or like the source of the centripetal force and the motion. The whirling rock on a string, the force provided by the string. So it's the tension in the string, right? So the force is the tension. The tension. What about electron orbiting atomic nucleus? We know that. Electron, and we have protons at the atomic nucleus. And what do you think the source for the force for the electron to stay in the orbit? You know the electron, you probably know this, you probably know this picture like this, protons and the electrons, that thing. Right? Right? So that is why we think electrons orbiting the nucleus instead of just flying off. Because of nucleus, what? Because of a force. Because of a force. What force? Electric force or electrostatic force. It's the electric force. So it's the electric force, that's the electric force, which is K times charge of an electron times charge of a proton divided by distance between them squared. Remember this thing? That's it. So that's the electric force. So the electric force keeps the electron in orbit. Right? And it's towards the center. It's the attraction, negative, positive. So for this one, you should say for this one that it's the electron nucleus electrical attraction, or just the electric force. Car cornering, friction. All right, so you rely on friction. When you are in a car, you are in the hands of physics. All right, and physics, the cars, is all about friction. You might think that friction is not a friend, is an enemy, but in reality, without friction, our lives will be miserable. Yeah, you can't move, first of all, in the car. So that's the first thing. You can't walk. See those guys, the astronauts in the International Space Station, how difficult life must be? I mean, it's fun if you have it for a couple of minutes, or let's say for a couple of hours. But imagine living like that for a couple of months, or for the whole life. In the space station, you know, those things, that they can't even, you know, shower, and they can't eat properly.
I saw this video.
How come? They can't. They just sponge things. You know, this is what they do. They use a sponge.
So the guy was trying to pray in
Pray.
Yeah.
You can use straps. You can actually strap yourself on the ground.
It's really spiritual, but the way he was doing it looks really funny. Like,
Yeah.
it's
The guy prayed there, like mamas.
yeah.
You need,
Use that thing to the floor.
So you need to be careful because the International Space Station actually completing one full rotation in 1.5 hours. Did you know that? 90 minutes.
Station.
One International Space Station, ISS, completing one rotation in 90 minutes. So the moment you start praying towards Kaaba, you know, by the time you finish, you'll be like facing somewhere else in the world, so you have to be very quick. But that's the excuse. That's maybe the only excuse that you should pray fast. You know? Anyway, I think as long as you are facing the earth, that should be fine. Yeah. No. So this is the Kaaba, and by the time you finish the prayer, you are facing China or something. Anyway, thank you. Then moon revolving around the earth, it's the attraction, gravitational attraction between them, gravitational force. Now, satellite revolving around the earth, it's the satellite earth gravitational attraction. What about this one, the vortex or rotor in an amusement park? We already talked about that. It's the reaction force from the walls. This one, it's this, gravitron. It's the gravitron. Rotor or say the gravitron. Gravitron should make sure you add gravitron. Gravitron, such a funny name. There's no such name in such term in physics anyway. All right, principle rotating the girl in the movie Matilda. Have you watched that?
Matilda. Roald Dahl.
Have you watched? It must be. Should we try that? I'm a principal, you're a girl.
Rotating, I think it's when she knows when she gives what's her name, Amanda someone and she's, I don't know.
She must be holding the girl from the.
From her head, she holds her from her head because she has two ponytails and she swings her around and flings her to the garden.
All right. Now,
I'm gonna try that.
that is a rotation. That's a circular motion. All right. And where do you think the force is coming from? Tension in their arms, or tension in the arms and tension in the hair, actually, in this case. Yeah, the arm of the principal and the hair of the poor girl. Playground swing. You are swinging in the playground. The force is coming from? The tension in the rope, the chains. The tension in the ropes, and earth revolving around the sun. It's the Earth-Sun gravitational attraction. All right? So, for all circular motion girls, it's important that you know the source of that force. This is critical. All right? The rest is pretty much. So, let's going back to this part, and let's write down the relations between them. Now, if this is the centripetal force and the net force, what do you think the direction of acceleration should be? The direction of acceleration. In the direction of the force, not the velocity, but the force. Because remember, F equals, F force equals mass times acceleration. This formula telling me that whatever the direction of acceleration, force must be in the same direction, because a mass is a scalar. It's not a vector. It can't change the direction. So whatever the direction of acceleration, force should be in the same direction. If you remember our previous, let's have a look at this one. Let's have a look at not opposite. The acceleration and velocity might be opposite, which means we have slowing down. If they're in the same direction, we have speeding up. Remember? Acceleration and velocity in the same direction, we are speeding up. Acceleration and velocity in the opposite direction, we are slowing down. But in any case, acceleration and force are in the same direction. Because of the formula, F equals ma. Force, acceleration is produced by the force. So whatever the force is, acceleration will be in the same direction, but that's net force, careful, that's net force. So the net force produces the acceleration. The net force produces the acceleration. It's like that. Momentum is equal to m times v, remember? So whatever the direction of velocity, momentum should be in the same direction. Look, changing momentum and all that, that's a different story. But the momentum of a car, the direction of the momentum of the car is the direction of the velocity of the car. Just like this. So in this case, we have to then say that the acceleration is indeed in that direction. So that's the acceleration. Looks funny. Looks funny, I know, but that's the case. That is the acceleration. The acceleration and force has to be in the same direction. Now we know that force has to be centripetal, and we know that acceleration has to be in the same direction as the force, and that's why we have this. So that is actually pretty much doesn't change in circular motion. So whenever there is circular motion, an object of mass doing a circular or uniform circular motion, I should say, velocity is always tangent to the path, and force, net force, and acceleration are towards the center. Yes?
So if we get a question saying describe the direction of acceleration in circular motion, do we just say it's in the same direction?
Yes, certainly. No, you just say towards the center.
Okay.
Center. All right, so let's write down what is what. Now, what we know, first of all, the centripetal force is the net force, and it's equal to m times a, which means our famous formula, the second law of Newton, still holds. Net force is equal to m times a. And the acceleration is v squared over r. Don't ask me why. All right, that's the acceleration. V squared over r. Sorry? Yes, it is. No. Remember, the acceleration used to be v minus u divided by t. Remember?
Yes, you know.
That formula is now this. The relation between acceleration and velocity, acceleration is change in velocity over time, remember? Acceleration is the change of velocity over time. Not anymore. Because in centripetal force, the acceleration is v squared, because v doesn't change, it's constant. It's not v and u. There's only one v. The magnitude is v. Squared over r. R being the radius of the circle. R being the radius of the circle. All right? And since this is the case, so this is not a new formula, what I'm writing is a new one. This is a new one. That's the only formula actually new here. And that then is going to be the centripetal force is then equal to m v squared over r. You see? M times a. Centripetal force is m times a. And a is v squared. So that is the formula actually. That is probably the only thing that needs to be noted here. That's new. That is the formula. That is nothing but inserting acceleration in here. See that? V squared over r. All right? Now let's move on to some questions. Here you go. That's a question. What do you think about that? It's a question about a mass attached to a length of string is moving in a circular path around a central point, or on a flat horizontal frictionless table. A table like that. Right? On this table, it's flat, that's important, and it's frictionless, and it's doing a circular motion. This is depicted in the diagram below. The string breaks as the mass passes point X. At this point, the string breaks. All right? Question. Which line best depicts the subsequent path of the mass? In which direction the path moves? Now careful. Remember, the ball, the object, the mass or the satellite, remember, wants to go in the direction of its velocity, but it can't because of the string, because the string is constantly pulling it towards the center, and it can't. Now the string says, that's it. I'm not going to provide the centripetal force anymore. You can go in the direction of your velocity, which is B. Not C, not D, or certainly not A, but B. Which one is most tempting in here? C, huh? No, C is tempting. No, honestly, C is tempting. Because you might think, first of all, visually, you think that it's a vertical plane, but it's not vertical. It's flat, horizontal. All right, so it's horizontal. So that's why the question asks you something, but it's actually, it pictures it on a horizontal plane. So it helps you remember, see, the question is actually some kind of misguiding you to choose point C. Even though it's a flat surface, you kind of think that, oh, it flies off. But it doesn't go through S, but C, but goes through B, because if you look at what happens, it goes in that direction, and it's supposed to be, let's say, instead of being here, let's say after a while, it will be somewhere else. Indeed, flying off the circle, but not like C, yes.
In which condition would it be part C?
No, in none of the conditions. No, in none of them. For X, no, it's just B.
So we can't, like, not for this condition, but like...
No, it's always, it has to be B. Before we go there, can you just go to this question here? Yeah, here, that one. I know, I'm sorry about that. It's page 21. Page 21. Page 21. Like. A similar question, or maybe 19, because I added some pages. A similar question, a satellite moves in a uniform circular motion. Uniform circular motion means that, girls, uniform means that velocity is constant. The magnitude, obviously, not the direction. Magnitude only. All right? Fine. The following table shows the symbols used in the diagram below. The diagrams are not drawn to scale. Good. F is the net force, V is the velocity. Which diagram shows the direction of force and velocity at the position indicated? Which one shows them properly? Is it A, B, C, or D? Which one you reckon can't be? Which one? It can't be D, right? Doesn't make sense. C? Nah, that's not. So we know that velocity is tangent, but this is tempting because sometimes this is tempting because.
But it says, but look, in the F, it says that the net force on the circle.
Net force on the
So
circle.
you might think that it's, yeah.
The reason for that is this. When you are taking a turn in a car, which direction you feel you are pushed? Towards the center or outside the circle? Outside the center. So that's always to think that there is such a force that is throwing you outside the circle. So but careful, that's not a force, it's your tendency. It's your tendency. Just like when the bus stops, you feel like you want to go forward, but that's not a force. That's because of your inertia. You just want to continue moving, even though the car stops. Then you hold something, you stop together with the car. Just like that, when the car is taking a turn, you just want to go straight. You don't want to take the turn, you just want to go straight. Yes, the car has tires and friction, but what you do is you either get the force necessary to stay in the circle from the walls of the car, or from the friction, or maybe you hold something in the car. All right? But you certainly feel like you are being thrown out of the circle. But careful, it's not the force. When you are taking a turn, when you are, let's say, this is the thing, and that's the car. That's the car, all right? And this is the car taking a turn. You know what I mean? You know, the wheels turn, the car is taking a turn, so everything is safe. The velocity, all good, friction, all fine. It's not going very fast. Everything is good for the car. But inside the car, let's say you are sitting here. Let's say you are sitting at the back. You're always sitting at the back. What do you feel? You feel like you are thrown out of the car, right? This is because this is the direction of your velocity, and this is the path, this is the intended path for the car. Or let me draw it, let me draw it like that. This is intended path, your path, circular path. So the car wants you to stay in this green path, but you want to stay in this blue path because that's your velocity, all right? And because they're not in the same direction, you kind of feel like you are being thrown out of the car. So for you to stay in this green path, you need a force, and that force comes from either from the friction between you and the seat, or you're holding something, all right? Or in worst case scenario, you are being thrown out of the outer, this wall of the car. Sometimes it happens. And then the normal force from the door produces you and tells you, no, you're not going anywhere. You're not going anywhere. You will stay in the path. Right? Anyway, let's move on. So that question was obviously A. But B is the most tempting. Going back to the question. Oops. All right. Yep, that's the next one. That's the question. All right. Calculating the acceleration and net force around a curve. This is a car question. A car of mass 1,200 kilogram is driven at a constant speed of 15 meters per second around the curve with a radius of 12 meters. Calculate. Can you draw the car and show the radius and the velocity in the diagram? Draw the car somewhere in the diagram. Draw the car, bird's eye view. Draw the car, the radius, velocity, and force. Right? Yep, wherever you want. Draw the car like that, like this, the car, and show the wheels. Show the wheels properly. You will be driving soon. Some of you already do. Draw the wheels. So which one was that? The mass.
Do we not include the mass?
Mass is a scalar quantity. It doesn't have a direction. So you just say m. But for force, you have to show a direction. It was centripetal force. So I can see most of you draw the car like this. With them, this is being the wheels. All right? Now, that's the velocity, right, which is 50 meters per second. And the acceleration, we don't know the acceleration yet, but that's the acceleration towards the center, and that is the force towards the center. Yep, these are the three things that always the case. The acceleration, or sometimes we use A with a C here, like centripetal acceleration, but doesn't have to be. All right, and the radius is, what is too big? And the radius is what? 12 meters. All right, so once you have this diagram, Kevser, tell me honestly, once you have this diagram, don't you see things? So you start seeing things, right? Once you do the hard job of drawing the graph, all right, then the rest becomes extremely easy. The question is, what is the magnitude of acceleration of the car? Come on.
So isn't it too high?
What does it mean too high?
Because the formula is mv squared over r, right?
No, for acceleration,
Oh,
the
that's the force speed.
acceleration is v squared. But it's good that you asked that question. Good girl, yes. Because she actually didn't believe what she found. She questioned. She said, it doesn't make sense. It's too big. Good girl. That's the way you do things. Because she actually found the force and she thought it's the acceleration. And she questioned it. Always question your answer and ask yourself the question, does it make physical sense? What am I doing? All right. So for acceleration, it's v squared over r. So that will be basically 15 squared over 12. That's 225 divided by 12, something 17.
18.75.
18.75. Let's take it as 19. 19 meters per second squared. We have the same unit for acceleration? Yes, we do. But to actually make sense of this, that is going to be hard. 19 meters per second squared, what is it? 19 meters per second increasing its speed every second? So it doesn't actually, that's the acceleration actually, but will be difficult to actually make sense in circular motion. All right, sorry? Sure. And for this part, the magnitude of the net force. Look, net force, yes, is the centripetal force. That is mv squared over r. Or if you like, m times a, which will be 12 times the acceleration, 19, and that gives you what? 22,500. 22,500 newtons is the force. Next question would be to you, Shadin. Where do you think this force is coming from? What's the provider of this force? That's the force, but careful. This is just like the, how should I say? It's not actually a force. It's just the sum of the forces. But where do you think this force is coming from for the car taking a turn?
Partially from friction,
Partially from friction, all right, and partially from?
the center of the circle.
You mean that's coming from the center of the circle?
And if you consider that the roundabout doesn't like center,
Yes. That is not partially but fully coming from the friction. So the friction produces this force. Because of friction, it's taking the turn. It has no connection with the center, but no ropes or anything, right? It's just the friction. It's the friction, only friction, that helps the car to take the turn, all right? So it's the friction.
I have a question.
Yes.
It says that there's a constant speed, but then we found that there's an acceleration. I don't get how's there's an acceleration.
All right. There is acceleration because the velocity is changing as a vector. As a vector, it's changing, right? There is constantly changing direction, right? So there is acceleration. What is constant is the speed, constant speed. They don't say constant velocity. If they say constant velocity in a circular path, it doesn't make sense. Because to stay in the circle, you have to change your velocity, right? Right? You have to change your velocity. So that's why velocity is changing. It has to change, otherwise you'll be going straight. So velocity is changing, and that's why there's a force. Right? The direction, but not the magnitude. The direction, that's why the formula for acceleration is very simple. V squared over which V? U or V? There's only one V or one U. That's the speed. All right? So here comes all the way to our very first lesson, the vector and scalar. Gizem, remember? Speed is the magnitude. It doesn't have any direction. It's not associated with direction. So, yes, it's constant speed. It's 15 meters per second everywhere. It's 15 meters per second everywhere. But the question is, how come we have acceleration if the speed is constant. We didn't say velocity is constant, we just say speed is constant, so that's fine. Speed being constant, having acceleration is just fine because the velocity is always changing in a circular path. What about this one? You do this one, come on. Again, show force, acceleration, and velocity. Force, acceleration, and velocity first. Force, acceleration, and velocity. By the way, it is a horizontal circle. Again, it's not like this, girls. If it is like this, it's not uniform circular motion. Has to be like that for it to be uniform. Uniform, like this. Not vertical, horizontal. Right, so that's the velocity, that's the acceleration, that's the centripetal force, and the radius is 1 point. Oh my goodness, what did you do?
What did I do?
I don't know.
Oh, it's gonna
Goodness me, what was that? Tangent. You know, you always study tangents in maths. Remember? Drawing tangents to circles, you did that, right? This is like tangent, you know, if you draw that's right angles and stuff like that. Remember? Drawing tangents to a point. Remember, girls? Drawing a tangent to a point in a circle. Do you remember how you draw? Do you remember how you draw a tangent to this point on a circle? Do you remember that? We have time, right? How do you do that? How do you do it? Tell me. No, don't do that. No, you do what? Sorry? This is a circle, and you want to draw a tangent at this point P. You want to draw a tangent at this point P. How do you do it? First, draw the radius. All right, so you draw the radius. And then what you do?
So it's the thing, you call it perpendicular to...
This, right? Then you draw a perpendicular line to the radius. And it goes through that point. Perpendicular. That's the tangent line. So you have been doing that in maths, but you didn't know when you're going to need it. Right? Yeah, well, what is this? Drawing a tangent to a point. It's pointless. But now, in physics, it does. Because the velocity, girls, the velocity, Kesar, the velocity is tangent to the circle at this point. And for the velocity to be tangent, yes, you have to draw the radius and then draw the velocity perpendicular to the radius. And careful, what do you think the radius is? The force. Hence, the force and the velocity are perpendicular to each other. This means the radius is the force towards the center, you know, the radius, force. So physics, this is force, and this is velocity, and they should be at right angles. So this is what I mean when I say maths is a slave of physics. Because you simply use it, right? What's the purpose of us?
It just helps us find the magnitude of the force, basically. Right?
All right.
Oh, you said maths?
No, maths. Yes. Wait. Now, going back to question. Show the velocity, acceleration, and the net force vectors on the rock, and then calculate the magnitude of the centripetal force and the acceleration. Fine. The magnitude of the force, let's do that one first. it's going to be mass times v squared divided by r, and that will be the mass, where's the mass, 0.25 times velocity 15 squared divided by the radius 1.5. 1.5, that gives you what? 38, let's say. Newton will be the force, and the acceleration will simply be like 200? 150. Wow.
How did you estimate 200?
4 times this, 100, I should say 160.
I thought it was like something like
Look, this is quite an acceleration, right? But that's the case. That's the case. I mean, when you're in a circular motion, you go through extreme acceleration. And this is actually how they test the astronauts in the old days. They used to put them in a chamber and rotate them in big circles and very fast. And the poor guy goes like that. Yeah, it used to be the way they test the astronauts. But this is actually, girls, this is actually 15 times g. 15 times the gravitational acceleration. And you know that watching those Red Bull, the plane things. Sometimes when they go dives and things like that, at the in the corner of the screen, it shows you the g. What is the g? And if you look at them, even the highest g that they go to is like maybe 10, 11, 12 maximum. All right? So 15g is quite high. If you go through 15g, all right, for a couple of seconds, you will probably pass out. You'll probably pass out. Why do you pass out? Because the blood won't go through your brain because of the acceleration. Yes, this is how you train the pilots. Yeah.
That's torture.
That is literally.
That's actually torture.
But someone has to do it to protect your country. Anyway.
So can I ask quickly, why are we like Luna Park? Like, what are you going to do?
Luna Park is nothing but physics. All right?
So are we actually like...
No, there will be worksheets and everything. So you'll be analyzing the motion as you have
So
fun.
this is the lunar
I mean,
where
it's-
they shut down for
it's-
schools, yeah?
Yes, that one. So it's not like we have to do it, but you have been asking for an excursion. I must admit, I was opposed to the idea, but the other physics teachers, no, come on, Hocam, let's have fun for once, and then whatever. So yeah, that way. So it's more for fun than being physics, but let it be.
When are we going next week?
Tuesday, 7th. 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 And it is the day we don't have physics, so you won't be missing from physics. Oops, sorry. And that's the only physics excursion in the entire year.
What?
Yeah, that's the only excursion. That's there's one more synchrotron or something. Yeah, there's one more maybe. I'm not sure. To a particle accelerator. Yeah. Thank you. Now things get a little bit fishy in this question.
How was the cars messed up?
Sorry?
How can a car have massive 1.5K? Almost 1.5K.
Yeah. Big cars.
Isn't that like really big?
No, it's not really heavy. 4-wheel drive are like that. A standard 4-wheel drive should be that much.
Really?
Yeah. Some of them are almost 2 tons. Big cars. So it's reasonable for a car to have this mass. That's the question. That's the question. So that's the velocity. So the car is taking a turn. That's the velocity. And that's the centripetal force. Right? So is the car taking a turn? Yes. The question is, what should be the force so that the car takes the turn? So you are going to assume that there is circular motion, and you're going to find the force. So we know that in a car taking a turn, centripetal force comes from the friction. So you find centripetal force, you find friction. Right? So that will be m times v squared over r, and that will be 1,550 times v squared, 30 squared divided by 7. So it will be what?
18,647.
The 19,000 newtons.
So isn't that too high of a friction force?
No, it's all right. It's all right. But let's say the tire can produce friction force. The tire can produce maximum is 1,500 newton. What will happen? What's going to happen? Do you have
You're going the direction of velocity.
Yes, so it won't take the turn. Instead, it will go straight, because to have the circular motion, you need this much, all right? And where do you think this is going to come? From friction. Do you think do you have a rope attached to the car that to keep you in the circle? No. That is the only source of centripetal force. So you need that much. But the tire company, the manufacturers of the tire company say that, look, the tire can produce only that much. If you want more friction, you have to have a bigger tire, or you have to make them flat, because flat tire, more friction. So they sometimes make them flat, friction increases surface and friction. Anyway, so in this case, if this is the case, there won't be any circular motion. So can we find, girls? Sirin, don't do that. Can we find then? All right, if this is the case, what is the fastest the car should go to safely take the turn? Yes. So when you are taking a turn, you're actually going through a certain part, an arc of a full circle. You know that, right? So when you are taking a turn, regardless of how sharp or how long the turn is, it is part of a big circle. All right? But you are just going through a certain part of it. You're not having the full circle, right? But just so every time you turn the wheel, you are a part of a circle. Every time you turn the wheel, you are part of a circle. So did you find the maximum velocity to be what? You're going to make this equal to v squared times mass over r is equal to centripetal force. And you then say v squared is equal to centripetal force times r divided by m. And you square both sides. That is the velocity for centripetal. We just drive it. 27 meters per second. So, you know how they write? Do you know how they write before you enter a curve, and if it's a sharp curve, they write maximum speed, like on yellow background. Yellow background, they write speed. It's not the speed limit. It's not a speed limit. But considering the sharpness of the curve, they calculate the safest maximum speed for regular tires, and they put it there. Girls, you missed that point. Girls, do you remember? Sometimes there's a road sign, girls. Sometimes there's a road sign saying 55. saying stop it. All right? You got it? Relax. All right? Let me do my job. I'll help her. Don't worry. Look. Sometimes going through some sharp curves, there is a sign saying 55 kilometers per hour. This actually is this. All right? So they calculate knowing the radius of the circle, assuming regular tires. Each tire will have a different maximum friction they can produce, but considering regular tires, they calculate the maximum safe velocity for that corner, and they probably take half of it, to be in safe waters, and they put it there. So it's very important that you stay in this limit taking a turn. All right? Try going a little bit higher than that. That's okay, but it will be very difficult to keep control. So this is not speed limit, which means you can go over this, but you're advised not to.
Oh, it's only at the exit.
Yes, exit speed, not the exit speed. Before turns, before sharp turns, there's a sign. It's yellow and with black writings. Yellow with black writings, I think like this, a trapezium. It's not a maximum speed, a speed limit sign, but it is the advised speed, maximum speed to take the turn. Because you're probably traveling at 80 around here, and you think you don't know how sharp the turn is. You know that there's a turn, but you don't know how sharp. That's why they want to remind you this is a sharp turn and you need to slow down. Yes, any questions? All good, Zara?
Yeah, I just wonder where you have to take
Yeah, I just made it up. Made it up. Like, this is the tire company. This is the company, tire company rating. We finished the question. Here, 19,000 Newton, that's it. That's the question. All right? I added stuff. All right, moving on. So they're done with the examples. Which is, all right. Don't worry about satellite motion, but there is also one more formula that we need to concentrate on. Yes, considering the car, considering the object is making a full turn. Yes. All right. We can also say that. Don't you think it's hot in here? All right. Can you see the object makes full rotation, which is the circumference of the circle in a period? Can we also say that? All right. So you remember that is the circumference of the circle, and that is the period, which means the time for one full cycle. Does it make sense? No, we are just doing it. Yeah, we had similar stuff last year. Sorry? Yes. Rotation? Yes, 1/4 cycle. 1/4 cycle of rotation. All right? So you are happy with that? Do you also remember this formula? Frequency equals 1 over t. And frequency is the number of turns, and period is the time. That's why it's T, capital T. It's the time for one rotation or one cycle, but frequency is the number of turns in one second. No, that's I use capital T for period. So, for centripetal force, if you remember, A equals V squared over R, and V equals 2 pi R over T. If we insert this in here, we will get 2 pi R divided by T squared divided by R, right? That will be 4 pi squared R squared divided by T squared R, right? And that simply is 4 pi squared R divided by T squared. So that's another formula for acceleration. Apart from V squared over R, an alternative formula for acceleration. All right, let me write an additional question. Sorry about that, girls. If an object completes one cycle in 2 seconds in a radius of 3 meters, find velocity, acceleration, and frequency. So remember, velocity is 2 pi r over t, acceleration is v squared over r, and frequency is 1 over t. The acceleration is 4 pi squared r divided by t squared. So it completes one cycle. An object of mass doing circular motion, completing one cycle in what? 2 seconds. How many turns it does in 1 second? 2 bar? If it takes 2 seconds for one turn, how long or how many turns in 1 second? Half a turn, 1 over 2, right? So the period is the period is 2 seconds, girls, and the frequency is 0.5 hertz, 1 over second. All right, what about velocity? Can you find velocity? Can you find the circumference of this circle? So can you find the circumference here? The circumference will be 2 pi r, right? That is, the circumference, 2 pi times 3, that is 6 pi, right? 6 pi is like 19 or something.
18.8.
At 19 meters. So it is 19 meters. The circumference of the circle is 19 meters. And you do that in 2 seconds. You do that in 2 seconds.
2 seconds divided by 2.
Exactly. So 2 pi r over t. And that is 19 over 2. That is kind of what? 9.8. 9.9 meters per second. And the acceleration, yeah, that's right. Acceleration is.
I gave the acceleration. Sorry, I think it's the acceleration.
But 19 divided by 2 is not.
Oh, it's 9.5.
It's 9.5 by 18.8.
All right, so 9.5 meters per second. And acceleration is v squared over r. That will be 9.5 squared divided by radius 3. And that will be something like 30. Right? 29.5 meters per second squared.
So, I got, you got the same thing as me.
How many minutes? 15. All right. How do you feel? Tired? A break? Yeah, sure. All right. Let's say a couple of minutes. Go.
They get different values, but it's quite similar with the different acceleration.
Sorry?
The 4 pi squared r.
Yeah. Because yes, that's right. That's because we did some approximation. It's not 19, and this is not 9.5. That's why we didn't use exact values. But to add two significant figures, we should be on the same page. All right? Yeah. So let's have a break for a couple of minutes. Why don't you just stand up and walk around, and we will then stop. So if you are still hyped up, you can have a look at these worked examples. When she comes back. Let's have the attention while we're having a break.
From the sample exam, we have to do questions that are relevant to like what we're doing in class.
Sure.
From the sample exam.
Sure, we will.
Because I went through it the other night and I actually looked a little bit difficult. Like some of the questions with the end, the short answer ones.
But we haven't done all of them.
Yeah, I know, but like some of the things like that, like from Newton and stuff from last year.
You think you have done it, but we didn't do it yet. That's the problem. I check the sample question. The questions are pretty.
So it looks so detailed, and it like combines. Yeah, doesn't it combine like different units and chapters and stuff into like one question? That's how I understood from when I looked at it. That's why I was like, oh my god, I know how to do A and I'm supposed to B. So not the sample one, that one. Sample reading exam.
So when are we planning to finish the book by?
Sorry?
When are we planning to finish the concept by?
Hopefully by the end of term 3. Hopefully.
End of term 3.
Yes. No, we can't finish before that. That's.
This one was really easy, so didn't we do this question in class? Yeah, it's the same question in class. So, some of them were easy.
Yes.
Stop.
Hmm? No. What do you mean? This is the attendance. Shule is not here. Shafika, Elif, and Ila. Oh. Why did you go?
Didn't tell me anything.
You wrote your name
Because she has this unstoppable feeling about physics she didn't want to miss. I know, Zara. Yeah, but you should have gone. So is it like English for why are you here?
It was voluntary. They just went to the library.
Voluntary?
Yeah. It was
Voluntary excursion?
Voluntary.
It was a
Like not everyone
we went in year 9. It's the same.
Why didn't you go then?
Because we went in year 9, so it's the same program. It's just showing how to do, like how to research.
Why did they go then?
Because they wanted to go.
Shule, Shefika, Elif and Dilara.
Yeah, remember we went in year 9, they took us into a room and they showed you how to research one type of thing. It's the
Ah,
same excursion. That's why it's different.
so they choose to go.
Like it's beneficial if you go.
I need to,
There's no point of going over the time.
I'll make them pay, don't worry. All right. No, it's good, it's good. It's good that you go. You should have gone. All right. Yeah, these are the questions, yes, sample, but we don't need to mess around with them. Can we? Yes, quickly. Have a look at these worked examples and let's proceed and start the satellite motion.
So then you bring it in and I just fill the whole page. I could have
Yeah, well, none of us can.
Sorry. All right. Now, since we have studied circular motion already, satellite motion is no drama. Yes, the satellite making, turning in an orbit, in a fixed orbit around the Earth. We know that it has an orbital velocity. That's called orbital velocity. Orbital velocity. And the reason to stay in that orbit instead of going straight is the gravitational force is the reason to stay in the orbit, and the centripetal force obviously requires a centripetal acceleration. So the only thing that is different is in satellite motion you don't need to worry about the source of the centripetal force. It's the gravitational pull of the central mass, right? A planet, a star, or maybe a satellite itself, because we have satellites orbiting satellites as well, the moons. Now, we have a set of formulas. Now, this is the first one. If you quickly turn the page, you will see the formula. So there's no drama, we already studied that. Because the speed is constant, all right, we can use that. It covers the circumference over the period, no drama here. Yes, Zara. Yes. They're on top of each other.
Yeah. Could you draw one line and have two arrows and write one on it? Sorry.
Like in this.
Yeah, like that.
Yeah, all right. Yeah. All right, and here comes the centripetal acceleration. Remember, we have studied this one already. And if you remember, gravitational acceleration was equal to gm over r squared. And that is also equal to the acceleration that we are talking about. So they're all equal. They're all equal. So there are a lot of formulas in this section, and you just need to pick the right one. So depending on whatever is provided, if V and R is provided, this is the one that you use. If R and T is provided, this is the one that you use. If the mass of the central object and radius is provided, this is the one that you use. For whatever is provided, you can pick the right formula. Yes? If the mass and the period is provided, no, you can't do it.
So it won't be like.
No, because if mass and the period is provided, can you do it? How come? All right, moving on, girls, moving on. And this is also the gravitational force. See, the centripetal force, girls, the centripetal force or the gravitational force is equal to mv squared over r, or gmm over r squared, or m times g. And this is when you use A equals v squared over r, and v equals 2 pi r over t. So if you put, or basically in here, you put that. So instead of v, if you put 2 pi r over t, you end up this. And that's the acceleration anyway. That's the acceleration anyway. Remember the previous page, acceleration times mass, and so on. All right? So these are basically the set of formulas. There's nothing, the only thing that's new today is this one, mv squared over r, mv squared over r. And since the centripetal force is equal to the net force, which equals the gravitational force, all right, you end up a lot of questions. So if the question is what is the force, depending on whatever is provided, you use, if the mass and the acceleration is provided, m times g. If the mass of the central object and the mass of the object and the radius of the orbit is provided, it's this one. And if the radius, period, and the mass of the object is provided, this one. And if the velocity, mass, and radius is provided, that one. So for force, you need 3 things. For acceleration, you need 2 things. For acceleration, girls, you need 2 things. 1, 2, 1, 2, 1, 2. All right? But for velocity, for force, you need 3 things. 1, 2, 3, 1, 2, 3, or 1, 2, 3, or 1, 2, if you know the acceleration, which requires 2 things. So that's 3 again. All right, why don't you look at this one? Come on. You are tired, I know, but let's do a couple of questions. The rest will be your homework anyway. Which one? No, we haven't looked at them, all right? Yeah, right. Where is a fly, a walking fly, a show jumping horse mid-jump? A show jumping horse mid-jump. Walking fly. A show jumping horse mid. Look, the horse is in the air, right? So 0, 0, 0, and that's walking fly. Because horizontal, no contact. For a no contact. It's not in contact with anything. It's in the air. It's in the air, right? Anything in the air, apparent weight is 0. Yes, anything in the air, mid-jump, half-jump, whatever, anything in the air, a fly flying, International Space Station, all right, or a horse in jump, or mid-jump, apparent weight is 0. All right, determine the orbital speed of the moon, assuming, look, for the orbital speed of the moon, assuming it's in circular orbit of radius that many kilometers around the Earth, take the mass of the Earth to be this, and is, all right, the orbital speed, now here comes the problem, the formulas provided to us, you see girls, there's no thing for formula. The only thing that we need for velocity is this, right? V equals 2 pi r over t, right? That's the only formula to find the orbital velocity, this orbital velocity. That's the question. All right? So it's useless because I don't know t. Right? So what am I going to do? Do I know acceleration? No. If I know acceleration, girls, if I know acceleration, right, I can use r and a to find v. But why don't we use, girls, why don't we use this? mv squared over r is equal to gm m over r squared. Can I use this? Yes, can I use this? So these are not giving me anything. They're not yet useless. But if you look at, if you make the centripetal force equals the gravitational force, you see the mass of the moon will cancel, and you will end up with V equals square root of G m over r. That is the orbital velocity. That's a very common question to find the orbital velocity. So it might be a good idea if you have this in your formula sheet. Orbital velocity is gm over r. Gm over r. Now, can I find it then? Yes, I know the central mass, which is the Earth. The radius is provided, so I can find the orbital velocity. All right? Now, on your quiz on Monday, there will be some questions from circular motion, but not like very deep into questions. But there certainly will be some questions from circular motion as well as 2.5, the homework. Oh, what? No. 2.1, 3.1. So let me clarify. Your homework, the quiz will be everything all up to 3.1.
1.1?
Right, 3.1. Yes, 1.1. Yes. 1.1. But from 3.1, not so hard. So, but there certainly will be some circular velocity questions. That's for sure. All right. And your homework is Chapter 2 review. Chapter 2 review. That's about 20 questions. Half of 3.1. Half of 3.1. All right? Half of 3.1. All right? But today's homework for Monday is Chapter 2 review and 3.1.
Oh, so the whole of 3.1.
Yes, 3.1 and chapter review. All right? But with 3.1, some of the questions you are having difficulties. That's fine, because we still will cover some of the stuff in 3.1. We have covered everything, but we haven't solved enough questions. We should need to do some more questions before I think it's okay to proceed. Anyway, yes, thank you for what? Yeah, not going to the excursion. All right, see you on Monday. Yes.
I used 9.8 instead of, I used 9.8 instead of 10 and I got it
But
wrong.
what you use here,
Negative, I got it right. I used the same, the math was right.
here's a mass.
Yeah,
Yeah, you did. Oh, no, 1.6. Is this the mass of a proton?
yeah, look.
Yeah, you got it right. Why did you use 0? Yeah, right. I'll fix it. Yeah, give it to me.
It's because you didn't write the answer in the box.
No.
It's not that.
Yeah, they don't do that. Yeah, so it becomes 15. Good girl. No, 20.